Добрый день.
Так, алло,
Да, я вас слышу.
хорошо. Так, а чё почти никого нет? А, ну сейчас.
А мы по правильной ссылке зашли? Может быть, нас в другом месте?
Наверное, да. А, я вообще-то даже... А, сейчас.
Я новые ссылки нигде не увидел, поэтому по старой зашел.
Да, я что-то не послал, надо было заново послать. Ну, это все время одна и та же ссылка, да. Ом, Ну, ладно.
Добрый вечер.
Добрый вечер.
Вроде я могу в этот раз писать что-то.
Да, Саша, Жень, если вы что-то говорите, то имейте в виду, что мы вас не слышим.
Точно.
Да, точно. Саша, у тебя микрофон выключен.
Сейчас
О,
слышно?
включен.
Да. Это что ли зумовская доска или что это?
Очень тихо слышно вас.
Тихо. Это доска от зума или что?
Это доска, не знаю, это моя тут. OneNote Microsoft.
То есть мне там нет смысла писать ничего.
Но вы на ней не сможете писать, да.
Да. Ну просто это самое.
Не, ну в прошлый
Бед-
раз даже докладчик ничего не писал. Тогда уж и
Нет,
слушателям.
ну докладчик это все равно ничего полезного не написал, а так это самое. Да. Значит,
Так и
изучили вы мои домашние задания?
А
Нет?
чего? В смысле?
Нет, ну конспект прошлого раза.
Ну, я прочитал вроде бы, по
Вроде,
крайней мере, про онлайн-лернинг. Ну да, наверное, все правильно.
наверное.
То же самое примерно, что я и говорил. Похоже на то.
Нет, ну скажем, из вашего объяснения, может быть, остальные все это поняли, но я не понял, например, что индукцию нужно применять не к первоначальному классу гипотез, а к уменьшенному.
Ну да, надо... Ну,
Ну, то есть, нет, может быть, вы все это и говорили 10 раз, но просто я не...
Чтобы получилось, ну, точки из-под дерева, да?
Ну, мы рассматриваем гипотезы только те, у которых там в корне там в одну сторону она идет.
Ну да.
Ну да, нет, но это вот вообще вам это всегда было понятно, а я это понял только после многократных разъяснений.
Сейчас, я думаю, что я сейчас не понимаю, о чем речь вообще.
Ну это вот
Ну,
то
может, я не
рассуждение.
знаю, если это, может быть, стоит повторить это, если... Maybe we should repeat the last part about threshold dimension and Littlestone dimension.
I don't know who wants to repeat.
I want.
There are... No, I mean, okay, I don't know. So I can repeat. So we want to show that the threshold dimension of the class is infinite. No, sorry. That if the Littlestone dimension is infinite, then the threshold dimension is infinite.
Maybe it's worth still explaining what are all these things, because you told it, but I'm not sure everyone remembers this.
Okay, so Littlestone dimension.
So H is a class of function on predicate on some set X.
Yeah, so H is the class of functions, class of predicates, some set X. Usually we call it hypothesis class. And then the Littlestone dimension H is the maximal D for which there exists a complete binary tree of depth D with internal vertices labeled by elements of the domain, where all paths to leaves are realizable by the class, by the functions from class.
So it works, it works like this. We take some X, which can be 0 or 1 in the class H. And then H is split into two parts. And then each of them, for each of them, we look for some other X0 or X1, different for different parts. That also splits this H. The part splits to two different parts. Two non-empty parts.
Finally, all the paths should be non-empty.
Yeah, finally we get a tree of height D with two to the D leaves, and each leaf corresponds of combination of values on different points, and this combination should be consistent with H.
Yes.
So it's a bit like Vapnik-Chervonenkis dimension, but here the second point depends on the answer for the first point.
Mm-hmm.
Yeah,
So
we have some initial point X, and then we consider a subclass.
Okay, that's clear. Maybe we can proceed to implication, to the second one.
Threshold dimension.
The threshold dimension is kind of the same thing. So it's it's the largest T such that there are T elements. You can find T elements of X on which all monotone functions,
all T plus 1 monotone functions are possible.
All T plus 1 monotone functions are realizable by H. So it just means we have well, I mean, with the, I mean, there is no particular order in principle on X. It's just we say, okay, let's fix X1, X2 in the order of their indices, and then we must have all zero function somewhere. I mean, then like 0, 0, 1, then 0, 0, 1, 1, and the end.
Uh-huh.
1,
Yeah.
1.
What I didn't realize last time, but understood only later, that there is a difference between these two definitions. The first one is somehow invariant if we, for example, take some points of x. It's not important. If we replace it by all functions by the negations, this doesn't change anything, because it's just important how we divide the functions into two parts.
But here it's,
And here it's very important. So if we, it's just 0, 0, 0 from the original.
Sorry, I don't understand.
No,
What's
the
the
original,
claim?
the first
I'm claiming-
definition.
I can make a claim if you consider for the class. I don't know how to know. So if you want to take a class H and you want to consider like all, I don't know how to say, complements of the functions from H. Right?
Not negations functions from H, but I want to change the value of all functions of H at some point x. So just at some point x, we reverse all values of H. Then
Yes.
the Littlestone dimension doesn't change, but threshold dimension changes, may change.
Uh-huh.
Do we have an example? And so what?
No,
what-
but I
what the idea-
think it is more or less, it should be somehow possible. But at least it's not
If you
obvious.
change it in one point, then
In one
Ah.
point, of course.
yes. If it's finite, it changes, but infinite value does not change. If you make your procedure at one point,
No,
you
if
can
it,
just
it
delete
can
this.
change by one, but so to say. But if it's infinite, then it's infinite.
Right. So you're saying that it can change by one, but it cannot change from finite to infinite.
Yeah, yeah.
And it's
No, just it's not just the first part. The first definition is just a bit more invariant than the second one. That's all I want to say. It's important to remember this.
Yeah, so we were trying to explain that if the Littlestone dimension, so the statement is that these things are for any class H, one dimension is finite is the only if, the other dimension is finite.
But I think I understand why one of them is at most the exponent of the other one.
Oh, but which one is at most of what?
Uh,
So if what is big, then something is big in what you can show. No, I guess the easy direction, if the threshold is big, then the Littlestone is big.
Yes. So why is that? Let's repeat.
Maybe Kolya can explain it now.
no, I'm confused now. Sorry.
No, if threshold is big, then there are points when all the monotone functions are possible. So take the middle point, and then 0 and 1 are possible. And
Right.
then H is split in one half. We have all the monotone function in one part and constant in the other part.
Uh-huh.
And still we can take the middle point of each part, which still if the half, take the half which is not fixed yet, and take the middle of this half, then we have 0 and 1.
Right. So that means that the threshold dimension is at most the exponent of Littlestone dimension.
Threshold is at most the exponent of Littlestone, or just Littlestone is greater than logarithm of threshold. It's easier to understand this.
Yeah. Littlestone is at least log of threshold.
Somehow, one can say that we have a hypothesis about the point which 0 are switched to 1, and then we can make a binary search, non-trivial binary search about this point, and it will have logarithm test steps, and still is not trivial.
Yeah. So let's try to explain the other direction. again.
Right.
So let me. So I want to explain that if threshold dimension, no, sorry, theorem. If Littlestone dimension is infinite, then threshold is also infinite.
If we have a big splitting tree, then we can find a big, not so big, but not small sequence of elements for the monotone, and when all the monotone functions are implementable.
So, and more or less, let's make it a remark that more or less we will obtain something that threshold dimension will be at least log of Littlestone. And in the other way we had, so there is so it's not, there's no, both bounds are like away very much from each other. Okay, so, well, formally you have to, I don't know, let's say just, so if you just, we want to show that for every t, there exists dt such that Littlestone dimension at least dt implies threshold dimension at least t.
No,
right?
we prove it by induction over t.
Yes, and we prove it by induction over t. Well, I don't know, let's just maybe do something for t equals 1. So for t equals 1, we just need one point where all monotone functions are realizable. But we just need 0 and 1 realizable. So which Littlestone dimension we need for that? Well,
I think it's question to Kolya.
Well, why is that?
Because he requested the proof.
I guess 1.
Yes, 1, because it's just we need a point where you can have 0.
Both values are consistent.
Yes. So now we are, let's say, we are proving induction step. So if I have, let's say I proved it for t, proved for t. And so there is some dt. And I want to prove it for t plus 1.
And dt becomes more or less twice bigger or something like this.
Yes. So I will take, well, I don't know, let's just say maybe that I will take a 3 So what's the proof? So I'm assuming that I have a, let's take just, I don't know, let's something like that. For just in case. So I have a tree. So I'm assuming that my Littlestone dimension is at least dt plus 1. Now I wanna extract t plus 1 points where I can realize all monotone functions by my class. What's the plan? So I take a tree of depth where of depth dt plus 1 where everything is realizable by the class, all the paths to the leaves. So then we will take any function from the class and the idea is that this function will either be the constant 0 or the constant 1 in the, well, it's not the idea, it's just I'm saying that like this will be either the constant 0 or the constant 1 on the resulting constructed set of points with of t plus 1.
Yeah, the plan is like this. So we take a threshold function for some subtree, and then all monotone functions are possible. But then we need that all of these functions, to extend our sequence, we need some point when all, for example, all of these functions are zeros. And also, then we get all the, we put at the beginning, and then we have zero anything. But also we need a constant function 1 then. So we need
to try to draw it somehow. So we will use induction on some subtree of that tree to construct t points where we can have 0, 0, 0, all monotone functions 0, 1, and 1, 1. But we need to extend it in a sense that either
one more point.
One more point, for example, like that. So we can extend it. We will extend either the point like from the right or from the left. We extend it from the right, then all these functions has to be 0 on that point.
1.
And then we will should have.
No, if on the right it should be 1.
Once, yes. And well, the other option is when we have
if it's on the right, it should be 1. Sasha, you wrote in a
yes.
In a different order.
So it is either like that,
and then you need additional function which is totally 0.
Or like that. The other option is that when I have this rectangle, I add a point the left on which, and then I need on which all these rectangle functions are zeros, and I need then add a function which is all ones here.
So there are two problems. We need a special point when we can have all zeros or all ones, and also we need a constant which is the opposite, either all ones or all zeros.
Yeah. And then the idea is very counterintuitive, so we will just take any function from the class, and this will be either this constant function or this constant function. So let's take any function, and let's consider all so on some points of my tree this function is 0, and on the other it is 1. So now the next step is to show that there exists so we can assume that we color every vertex. So what we will first show is that there exists a large monochromatic subtree. So
embedded tree.
Huh?
Embedded tree. It's not exactly subtree, but
Yeah, so embedded, so I mean I can take so the subtree, what we understand is that we just have a point and then we can take any its descendant on the left and any its descendant from the right.
Maybe on
same
different, no, maybe of different levels.
Uh-huh.
Yeah, I
Just
mean
draw
maybe of different
something.
levels and then recursively like that.
But what is
So
important to understand, which I didn't realize last time, that if we have an embedded subtree like this, it's again a valid splitting tree, because we can just consider only these things, and they all made non-trivial divisions at every point.
Mhm.
yes.
So even if it's not a subtree, we still have a valid splitting
The
tree.
idea is that I can have a vertex, there is some x, and I can go to the left or I can go to the right. But instead of taking as a next vertex its immediate son on that direction, I can take somebody below in the tree. And the same thing on the right.
Uh-huh. And the depth should be dt, right?
The depth should be dt. So we will show a lemma that more or less says that if I have a tree colored in two colors, then there is a monochromatic embedded subtree of depth
Approximately half.
half of the initial. Well, there is maybe some minus constant, so that's why I took 3 here.
Uh-huh.
No, you don't need the constant, okay, but it doesn't matter.
Yeah, so
Okay.
then we will take, so let's assume that we have proved this lemma, so this combinatorial. So the combinatorial statement is that any tree colored in two colors have a subtree embedded a large depth. It has a monochromatic embedded subtree of large depth, namely more or less half of the initial tree.
Uh-huh.
Then we take it for our function. It means that we either obtain a subtree where where h is 0 everywhere, or h is 1 everywhere. So
Our
I mean, the initial colors are obtained by
our
value
function, special arbitrary function h, which was fixed in an arbitrary way, still is constant on the subtree.
Yeah.
So it's a good news, because then it will be new. We can take our new sequence inside the subtree, and then the last line will be constant, 0 or 1.
Yeah, let's say that h is constant 0 there. So then indeed we will construct our first t elements using just elements from that subtree on which h is all 0, and it will be fine.
No, actually not from the subtree, but from its half.
Yeah,
We need that.
Yeah, so then the next idea, so what we can do is that we can take the root of this subtree x, and I will say that I'm actually will be x, this root will be added to the right. This will be xt plus 1, the new element. And now,
So now we are thinking how we made this column of ones.
Yeah.
We need not zeros is just because all the colors are 0, and the question is how we get ones. And the answer is
Yes,
we just look at the
update-
subtree when it's 1.
Yeah, so we take a subtree of x corresponding to value 1, and we consider now all functions. So we know that every path in that tree is realizable, in particular in our class. In particular, we can take, but we will apply induction step to, so we will restrict our class to x and to the numbers that we can see here. And we will take, and for each path here, we take a function from our class that realizes it.
No, we just consider only the functions from H which are 1 at x. We just take more or less half of our H and apply induction argument to this smaller H and the right subtree.
Yeah, and just want to say that I also want to make sure that I will obtain x1, xt just from elements of the subtree. Not so then and for that I'm just saying that what I can also do is just restrict my initial class to a smaller domain, which consists just of numbers that appear in this right subtree.
No, Sasha Shane, the problem is when you restrict the class to functions which are 1 on x,
Yeah.
you do not have any information about Littlestone dimension of this class.
No, we have a, because we
No,
still
we have a large subtree. We have a subtree of one dt minus 1, dt plus 1 minus 1.
Okay.
And of course, we prove by induction that we can find our sequence among the vertices of the splitting subtree. Yeah? That's what Sasha is saying, that we can restrict everything to our, also restrict all the x to only the subtree vertices if needed.
Mm-hmm.
Yes. Okay, so then there was what I missed is that there is a combinatorial statement that says about the monochromatic subtrees, and more or
So
less
the proof is finished modulo the combinatorial
Yes.
statement.
combinatorial lemma that we need. So let me state it like that. So if depth p plus q minus 1, 3 is colored into 2 colors, then either it has a depth p subtree of the first color,
So depth is just height. So if tree has only root, the depth is 0.
or depth q subtree of the second color. Well, all the vertices have the second color. And this is kind of Ramsey.
So
is the
how you
statement
measure the depth? It's, for example, if it's only root, depth is 0 or 1?
depth is 0.
But then I guess it should be p plus q, not p plus q minus 1. Okay, but doesn't matter.
Well, let's prove it and see. So this is so if let's say so the proof is by induction on the sum of p and q, right? So I don't know if p and q are 1, so it's easy, right? So we have a tree of depth 1, and we need a monochromatic subtree of one of the colors of depth 1. Well, it's just this tree itself, depending on the color of the root. Is it clear?
No, I don't understand. So you don't want the leaves don't have the color in your notation.
Leaves don't have the colors. It's only internal vertices that have the colors. So
okay, it's a bit strange, but
no. We have a misunderstanding then, because it's important that in the trees that we apply here, there is a difference between leaves and internal vertices, because leaves have internal vertices have axes, and leaves don't have any labels. So by subtree in particular, I mean that leaves of the subtree are necessarily leaves of the initial tree.
Okay, you can also do like this. Yeah.
Yeah, so, and then if we want to prove it by induction, so let me.
So
the idea is that
in this simple case, both cases occur or not?
no, just one, because I mean, if let's say that the first color is red and the second color is blue. So if this is a red, if the root is red, then you obtain a red subtree. So, but not a blue subtree, obviously.
But wait, initially we color only leaves. Why do you say that the root is red?
No, initially, quite the opposite. We color only internal vertices.
But you said that the color, we have some age. And
We
the
have
color,
some age, and the color of the internal vertex is the value of age on the number from that vertex, on the x.
okay, the color of age. I see. Sorry. Okay.
Yeah. I think I will have to repeat it next time once again.
Okay.
But so the point is that, okay, well, now you will have to finish the proof somehow, because so we are, let's say, so we proved it already for all p and q's with smaller sum. And let's say I have some tree of depth p plus q minus 1. And let's say that it's red. It has a red root. So we need in that sub, in all this tree, we either need a red tree of depth p or a blue tree of depth q. And we want to apply induction. Well, I would say that we somehow need to apply induction to the subtrees. So how the subtrees have depth p plus q minus 2, right? How you finish the proof?
I don't know.
Well, you need to, so there are two options you can apply. So you have p plus q minus 2, right? So you can, well, I guess you can either try to obtain either a red subtree of the, so you, well, this is like, you can represent it as p minus 1 plus q minus 1, or you can represent it, you can apply induction either to this splitting or to this
Right.
splitting. What do you think is a better idea to do in that case?
Maybe it depends on the color.
Yeah, that depends on the color of the root. So let's say it's red, and red corresponds to number p, right?
So we need p. So maybe it's p plus q minus 1 if we need p for red.
No, actually, the idea is that either we can find in subtree, we can find either P and Q. If P and Q are possible, then it's okay. But if it's not possible, then it means that we can find Q minus 1 and P minus 1 as we want. Both P minus 1 and Q minus 1. And then having the root, whatever the color is, we can complete it to a tree of size P or Q, just in one sentence.
So we consider both splittings, and for both we apply the hypothesis, right?
Yeah, so
Yeah,
either
must
there
be.
there is correct thing exists in one of the subtrees, then we are happy anyway. But if not, then at least then p minus one and q minus one both exist in both subtrees because we just have one smaller depth, and then we can for every color of the root we can still extend it in both directions.
No, we can extend it only in the direction of the root, of the color of the root, but that's fine.
Yeah. No, in both left subtree and right subtree has the right the continuation. That's what I meant.
Yeah. Okay.
No, it's not clear. I'm sorry. Can you repeat it once more, please?
Сейчас, давай я попробую сказать, я прошу прощения, сказать коротко по-русски. Значит, мы ищем либо P дерево, либо Q дерево. Есть возможность найти их в поддеревьях по индукции. Но
почему? По индукции же...
По индукции мы можем применить к паре PQ-1 и к паре P-1Q.
Ну, да.
Если хотя бы в одном из случаев мы находим P или Q, то все хорошо. Если нет, то в обоих поддеревьях мы находим P-1 и Q-1.
Сейчас, а почему хорошо, если P или Q?
Потому что они будут уже и в исходном дереве будут.
Ну, тогда выбросим корень из другой.
Да, будут вложениями просто там.
Ага, а если есть P-1 и Q-1, то что делать?
То тогда в обоих поддеревьях есть и то, и другое. Тогда какой бы цвет ни был у корня, мы можем от него продолжить использовать соответствующее поддеревье и получить P или Q.
Ну, в первом случае одно, а во втором случае другое.
В первом случае мы получаем P, но и лемма утверждает, что есть либо то, либо другое.
Понял.
Sorry, I didn't know if anybody needs.
Okay, thank you very much.
Yeah, okay. Well, I guess I will have to repeat it sometime once again, but because it was all okay, but then we started thinking, well, what are the leaves colored? Are the internal vertices colored? And then it was
No, I agree that no, if you say this theorem just for trees, it's more natural to color the leaves also. But in our case, we don't have the leaf colors, so this is why I was confused. Sorry for this.
So I guess let me try to say something about computable learning, something simple.
Something simple is always welcome.
Computable online learning. Well, so let me remind how the normal online learning goes. So we have a class, again, hypothesis class, and then the assumption. So and then there is it's supposed to. We consider essentially a game where there is a learner, where there is adversary. The adversary first chooses a function from the class. Well, I mean, you can imagine that adversary just chooses everything in advance. So it chooses a function and then some sequence of elements, infinite sequence of elements from the class. Then it gives x1 to learner. A learner is supposed, so it's like a question, what is the value of my function that I guessed on x1? Then the learner gives some prediction. Well, he
0 or 1.
Something, and then adversary reveals the real value. Well, okay, or it says, is it wrong or right? And then it goes again, gives x2, learner gives y2, adversary predicts the same f of x2.
So unlike this pack learning, there is no distribution, it's just a game.
Yes. And well, we say that H is online learnable with D mistakes. If there is a strategy that guarantees that, so that's what we had discussed last time. There is a strategy of learner that guarantees that
Whatever the sequence is, there is at most D errors.
there is at most D times where he was incorrect, where they were incorrect. The learner. So computable learner is just a computable strategy in that game. So, well, what precisely is the position? The position where you have to make a move is some finite number of rounds, where basically, essentially, you have the position can be described. You give some sequence of elements of the domain with the value of the function, and then the next number where you have to predict the value. And computable strategy is just that it is the strategy for which there exists a Turing machine that
So we consider only the learner side. Adversary does what the worst thing for learner.
yeah, adversary, no computability on adversary so far.
Yeah.
Well, I mean, and then during the don't think about computability of adversary.
Okay, no, I think that the computable learner
more
is
or
a
less
very
clear.
natural thing, yeah. Just an algorithm which performs the learner's duties.
So we will. I can point out that in principle we will consider two. Well, in general, so we consider. So I mean, I'm just saying that the learner doesn't have is not necessarily a total function, computable function, because in the game not all possible sequences like that can appear, right? Only realizable. So we will consider, but we can also consider a stronger restriction that the strategy has to be computed by a total Turing machine.
No, it's
Does this-
not that natural, but we can if we want.
Yeah.
And
No, I
then
mean,
you
it's
will
just
you probably you should say there is a computable dimension which is the minimal number the errors for errors for mistakes for computable strategy.
well,
And
that is not true, unfortunately, and that will be. But let's start from something simpler. So the first,
yeah,
I mean,
that's
you know.
simpler.
So what I want to say is that if I have a computable learner with at most d mistakes, possibly partial, right? With most d mistakes. Well, then the functions from the class are computable. Then computable learner with d mistakes for h implies that h consists of computable functions.
this is more or less obvious because every function can be learned in finite time, and after that, we don't need any new information, and no, we should.
Yeah, okay. Is it clear more or less?
No.
somebody.
One. I guess if we remember.
So I guess the proof should go like that. So you take any function from the class. And
You show
well,
only half of Aya. Yeah.
is it
Now
fine
okay.
So I take any f from the class, and let's consider a game of my computable learner with adversary that gives the natural numbers.
Enumerates all x.
Yeah. I mean, let's yeah, I forgot to say. Let's say we will consider that if x is countable and for x
Consists of
obviously
some
there will-
constructive object or whatever.
Yeah, let's say natural numbers, for example. So we consider this game, right? We can almost, so like what we need, this play of that game, if we would know this game, right? This is enough to reconstruct the function, right? Because in particular, the play of the game includes the values of the function on all the numbers.
Yeah, we just wait until all the errors are made, and after that we compute everything using finite information. That's what you want to say.
Yeah, so we just, but what we don't know is where we will make mistakes. But since we make just at most d mistakes, we can indicate where we make mistakes, and even that is just enough to simulate that play.
Yeah.
And this gives it implies that this function is computable.
Yeah, but still we can have a very simple computable learner with at most d mistakes, and still H can contain complex computable functions.
Yeah, I mean, you can
Because
take
this
any
amount of
H
finite
consists-
information is not bounded.
Yeah, I mean, you can take any computable function on its own as a singleton, and then this class will be computably online learnable. You just at least
No, but learner will be complex somehow. It's not what I say. I say that a simpler learner can work for a class which contains complex functions. For example, if H contains functions which are all 0, 0, zeros and at some point 1, 1, 1, 1, then complexity can be arbitrary, but at least in this way, if they are given in the order 1, 2, 3, 4, and so on, the learner is simple. It just predicts 0 when it says 1, then it's. But if it's in different
I
order,
don't
it's
know.
not obvious.
What statement are you trying to prove now?
No. I wanted to show, but I now I see this incorrect. I wanted to show that the complexity of a function in a class is not bounded by by complexity of the learner.
Well, I don't know how these things are you exactly have in mind in the definitions. What is the complexity of the learner?
No, just the complexity of the algorithm.
Commagolov complexity?
Yeah. No, I thought that we can consider functions which are 0, 0, 0 and then 1.
No,
And
I
they
mean,
can
we
have
need,
arbitrary complexity,
we
but
need
if
a
the
kernel
learner
for
asks...
the learner, and also the places where this guy makes mistakes, and these things can be arbitrarily complex compared to the program of the learner. And I mean, in general, there can be some computable learner for infinitely many functions. So that will have arbitrarily large complexity in that sense. So
Yeah, but still, I don't know an example for a infinite class where when some
where what?
then some learner makes at most d mistakes. Can you give an example?
Example of a class with computable online learner.
Infinite class.
Yeah, okay,
Yeah.
I can.
Yeah,
So
just
you can
say.
consider indicators of natural numbers.
Yeah.
So functions from
And the learner always says zero, and if learner is wrong at one point, then he knows everything.
yes. So and in particular, yeah. So there's an infinite class. There is an infinitely complex natural numbers. I mean arbitrarily complex natural numbers that are more complex than the algorithm for that learning. Okay, let me now state another obvious lemma that
Yeah.
if you consist of computable functions and your Littlestone dimension is finite, it's not enough to have computable online learning. So stated somewhere. Well, I don't know. Maybe let's start a new one. Position. Finite. So we have two necessary conditions for a class to have computable online learner with a
It should consist of computable function and it should have finite dimension.
Yes.
But they together are not enough.
So finite Littlestone dimension and consisting of computable function doesn't apply computable online learning.
But if you say that it's obvious, maybe someone can guess why it's true.
I should say that it's Hasrati and Ben David result. So this was in some paper, and it was a theorem that.
Oh.
Well, okay, maybe it's not that obvious. So, well, I would say that finite Littlestone dimension and finite and consisting of finitely supported functions is not enough for computable online learning. So computable, they will be computable, just they will have finitely many ones.
Mm-hmm. But if they have finitely many ones, you can just predict zero, and each one creates an error. But then you just are still predict zero, and then you have finitely many errors. I don't understand this.
But it's not bounded for any d.
So each contains finitely many non-zeros, but
yeah, I mean, I can also make, yeah, I mean, in that sense, you are right. But if I want to make every learner make infinitely many mistakes, or so, then I would need indeed computable functions. I mean, not finitely supported. But let's first make sure that there is no, so we want to give an example, an example where no computable online learner makes, where there is no D, and no computable online learner that makes at most D mistakes.
And still all functions are, a dimension is finite, and all functions are finite.
Yeah, and the dimension will be even 1. But let's first discuss, there is one subtlety here. I mean, some kind of subtlety, like how to fool a potential computable online learner. You can have a learner, in principle, it can, well, for example, it can be a program that doesn't halt anywhere, right? Or, so if you put something to your class such that this learner doesn't halt on that, then already also, you know, this learner, this thing cannot be a computable online learner for your class, because by definition, the learner has to halt on everything that is realizable by the class. The other option, you can fool the learner, some learner, you can put into the class something on which this learner makes D mistakes.
More than D mistakes.
More than D mistakes.
Yeah.
So how we will make, well, and then, okay, having that, let me also say how we will ensure that our class will have Littlestone dimension at most 1. It's just the function. So I will make sure that our H, in our H, functions have disjoint support. Well, it means that basically, if I have value 1 somewhere, then there is only a single function that can be consistent with it. This implies that the Littlestone dimension at most 1, because I can predict 0, and then if I see 1, I know there is only 1 function left.
Yeah.
So the idea is to fool every potential pair L and D. So we have so for any pair of potential computable learner and D, we will assign a block of numbers where, well, I mean, let's say of size D plus 1. And I will put, so then imagine that I have some set of numbers of size D plus 1, and I consider all functions on that block. There exists a function on which this learner makes D plus 1 mistakes, right? You just consider a function where the learner is always wrong.
Sasha, do we assume that D is fixed now? So for each D we construct that class.
No, we construct a class for all learners in D, for all D.
No, we need a class which doesn't have a learner with any bound.
But it seems that you have fixed D.
No, but this class is constructed some kind by diagonalization, not diagonalization, but for each pair of algorithm and D, we just make some block when it fails.
Ah, I see. Sorry.
So it's possible that learners give only points in this interval, and then our algorithm is forced to provide at most D errors, and this is not possible if the interval is T plus 1 elements, because we can make whatever we want. And then outside this thing, functions still be 0. So it will be finite, and they will have disjoint support.
Right. Is it clear more or less now? No.
No, I know.
Say it again. For every pair LD, we define what?
We find some interval where this pair will be fooled.
Okay, how do you find?
We just take an interval of size d plus 1 somewhere.
Mm-hmm.
And for different pairs LD, these intervals are disjoint.
Okay.
And
On
then,
that interval, we take a hard function for L, in the sense that we take a function on that interval in which L makes d plus 1 mistake.
And how do we do that?
Well, it just exists because you can consider a play where you give the first number, L predicts something, but then you had different value, then you give the second one, it predicts something, you give the other value, and so on.
Uh-huh, I see. Mhm.
Right. So next thing that I want to explain, another very simple thing about the correspondence between total computable online learner and partial. So basically, if I have, well, I just want to give an example. Well, maybe you can also already now give an example like that. Basically the same idea. Example of a class which is computably online learnable. But not by a total learner.
so it's computably online learnable for some d, and not a computer learned by a total learner for any d.
Yes. It will be computably online learnable with one mistake. But the computable online learner has to work in uncomputable time bound because it cannot be extended by total to a total function. So the idea is the same. We have to use disjoint blocks again to fool any potential but now total learner. But well, in some sense we have to fool all total learners, but still there has to be a partial learner. How we do that? So again, I mean, the construction is more or less the same, right? So I take any potential learner L and any D. I don't know where L and D is
L
total
is
or not.
total, yeah.
So, but what I will try to do is that now, I mean, I assign again at some block in some interval of with d plus 1 numbers. I try to give it I give it the first number from the interval to this L and start running it. I mean, and then if it never halts, for example, then I'm fine because it's not a total learner and I don't have to fool it.
Yeah.
But then, okay, let's assume that it halted on some on the first number, right? And it outputted some value. I say to him, you were wrong on x1. Now predict the value on x2 and run it again. Again, if it doesn't halt, I don't care because it's not a total learner. If it halts, I continue. That way, if it halts for d+1 rounds, what I do, I add to my class the function that that is consistent with what I was saying to learner in that process, where it's consistent that it made d consistent with the fact that it enforces d+1 mistake for that learner.
Yeah.
And I do that in parallel for all L and D, in parallel for all pairs L and D. And it's already clear that this thing is not learnable by a total learner.
Right.
Well, because for any total learner, L, and for any D, there will be a block. This total learner is total, so the process will be finished, and I will put in some function into my class on which it makes d+1 mistakes in some way. But for partial, the argument works only for total learner, because if a partial learner, it can be that I have some partial learner L and it never stops, and I never add anything to my class that would fool it in that block. I only add it if and only if the fooling has been done completely. We fooled it to the end. But what I'm trying to convey now is that at least we have shown that it's not learnable by a total learner, computable learner. It doesn't mean that it's learnable immediately, that it's learnable by partial learning. But is it clear that it's not for any, so there is no D and there is no total learner that learns this class?
By construction.
But if learner is not total, what you do with the function and the block?
Well, basically, essentially, I'm enumerating. So my class is enumerable of functions. But I mean, this will, in a sense that this is a class of finite supported functions. My class will be enumerable, and they will have disjoint support. So what I'm doing is that enumerating my class.
Mm-hmm.
So if L doesn't halt, let's say on x1, then I never put anything to my class.
Yeah. But if it halts on x1 but not on x2,
also don't put it. It has to go all the way to the end. It has to halt d+1 times such that I can something that I know that it would make d+1 mistakes. The point is that the total for learners that I care, for total learners, it will happen for any block and for any D.
Yeah, and how you partial learner will do?
The partial learner, I noticed that this property, that this class is in some sense enumerable.
Yeah.
I mean, for example, I can enumerate all functions in the sense I can enumerate. Well, my functions are finite supported, so there's essentially finite objects, and I can enumerate all of them. And the other observation is that they have disjoint supports. So what I have to do? Why it's partial learnable? So what I predict, I don't know, let's say in the beginning.
You try to find the function whose support includes this first x1, right?
No, I mean,
no, but if there is no such a function, you should still predict something.
So let's start by predicting zeros. I mean, why this class is learnable without any computability, first of all? Because the functions have disjoint support. So first I can predict 0, and when I'm wrong, there is only one function.
Yeah. And then when you know that you are wrong...
But in the realizable case, it means that now if I have 1, I can wait.
You know which learner should be responsible for this interval, and then you just run the process and see that wait until the function is finished and then do it. Yeah.
Yes.
And also you can start with predicting one. It doesn't matter what you predict actually.
No. If you predict one, then your prediction could be wrong, assuming because there are other functions for other intervals, which are total zeros here.
So this is not symmetric. Other functions are total zero.
Yeah, and so you should be safe for the functions from other. And as soon you made one error, you can you know which function you have.
Yeah. So then if you received x on which the value is set, on which the adversary says the value is 1, you can just wait until you enumerate the function that agrees with that, and then this is your function. But the problem is that this learner will not halt on something that on some block for which we never put anything to our class. So it's not a total learn.
Why it's not total? Say it again.
Well, I mean, so for example, because you can give it some x and you say from some block on which there is no function from my class with value 1. And you will enumerate the functions from the class and you will never find the function that is 1 on that class. And then you will not do anything.
So your answer will be incorrect, but we do not require that it's correct. I mean that the opponent cheats because there is no such function in the class, but still the learner should be defined.
So basically what we have so far, a simple picture. That total implies partial, of course, but not the other way around. And it implies finite Littlestone dimension plus computable, but not the other way around. So next, what I want to add is effective Littlestone dimension. And our hope was initially that it characterizes total computable learn if it must be mistakes, but it's not true. So let me define it.
But have we seen already that partial implies finite Littlestone dimension?
No, I mean it implies just
no,
because
but any learner with
learning.
finite many error implies finite Littlestone dimension.
I see.
By definition of Littlestone dimension.
Sorry.
Yeah, so effective Littlestone dimension of H
is the maximum number of errors for over all learners.
No.
No.
Otherwise, it would be trivially the same thing. So, what we want to define is that well, you can. Let's recall how the Littlestone dimension is defined usually. It's the maximal D such that there is a tree where everything is realizing.
Oh, so there are two dual definitions: one with learners and errors, and other with tree.
Yeah, and there
and
is
you say that if
dual definition that it's the minimal D such that in every tree of depth D+1 you can find a non-realizable branch.
Yeah.
So the effective Littlestone dimension is the same thing where you want this to be efficient. I mean, there has to be an algorithm that, given a depth d+1, finds a branch non-realizable by the class. So it's the minimal.
So somehow you have two dual characterization of Littlestone dimension with trees which gives lower bounds and with learners which give upper bounds. And now what you say that if you require both of them to be effective, then they are no more dual. Yeah?
Yes. So effective Littlestone dimension of H is the minimal D such that there exists an algorithm such that which, if you give it a depth d+1 tree, outputs a leaf
Which is not
not
realized.
realizable by H. The first, well, I don't know, let's say just that the usual Littlestone dimension can be smaller. I mean, is at most the effective one, right?
Maybe plus or minus one.
Not why
No.
minimum why minimal D? Is the maximal D, I guess. We want the tree to be big. If we have a bound from below, then we should take the maximal bound, no?
That's a bound from above. We want to show that it's the minimal D for which we cannot find the d+1 depth tree where everything is realized.
Sasha, this implies actually that the Littlestone dimension is larger than D, right? Sasha,
Yeah.
larger than D, so there should be +1 or -1.
No. Because the usual Littlestone dimension of H can be defined as the minimal D such that in every
There is no
d+1 depth tree,
yeah.
D+1, I see. Sorry.
there is no there is a leaf, there is a
Right.
non-realizable.
So it's, no. So I was wrong. It's not effective.
So D+1
Lower
is
bound.
included in the definition. Sorry, I
Yes.
didn't see.
Basically, we consider all natural numbers, and for each of them we indicate whether there is a tree of that depth where everything is realizable, right? And then obviously, I mean, this is like for some initial fragment of natural numbers, this is true. And then starting from some number from d+1, this is false, right? You cannot find a tree where everything is realizable. So what you can say, it's either the maximal number with the plus or the minimal number with the minus, like minus, or like the minimal number such that this number +1 is with the minus.
Yeah. So let's see. We have the Littlestone dimension in with two definitions which are the same, which are dual and they coincide with each other. And then you try the effective version of both definitions with the maximal number of errors for computable things, learners, and this new. So the both effective versions are bigger than the normal definition, yeah.
A normal definition, what do you mean?
No, so non-effective. So there is Littlestone dimension.
Yes.
And it has two definitions with learners and with trees.
Yes.
And now you consider effectivization of both of them.
Yes.
And for both of them, you may get some number which is bigger than Littlestone dimension.
Yes.
So they are both of them are upper bounds for Littlestone dimension. And
Yes.
what you say that this upper bounds are not related to each other, or what?
No, there is some relation, but only in one direction. So if I have a total computable learner with at most d mistakes, let's write it somewhere. Observation. Total computable learner with at most d mistakes implies that effective Littlestone dimension is at most d.
So there are actually two versions with learner, for total learners or for non-total learners.
Yes.
Yeah. So the total one is bigger and it's bounds for this version of effective dimension. Yeah.
I mean, it's in which sense it's bigger?
No, it may be bigger, it's just.
More restrictive. So
No,
why is
total
that? So
total learner is more restrictive, so it makes more error.
yes. I mean number of errors. Yes.
Yeah.
So let's say you have a tree of depth d plus 1, and you have a total computable learner which makes at most d mistakes on the class. How you find a non-realizable tree?
No, I just try to apply this learner to whatever the answer it produces before. So I apply it to the root and say he claims
Yeah, you
something.
find branch on which this learner makes d plus 1 mistakes, and you say, okay, this is not realizable by the class because
Yeah.
the learner made d plus 1 mistakes on it.
Yeah.
So let's write it. Effective Littlestone dimension. So we know that total implies that. I mean, it's rather easy to see that more or less. So remember the argument that partial doesn't imply total. More or less the same argument implies that it doesn't imply partial doesn't imply effective Littlestone dimension.
No, but
Because
just
of the total nature. This thing has to be total. So like for each block you can
let me draw some picture which then you can comment on. So I think I can draw in zoom over this. So we have this Littlestone dimension, and then we have errors for non-total learner computable and for total, two numbers. And
yes.
We have a third number which is called effective Littlestone dimension. Somehow, I don't know why you choose this one to call it effective Littlestone dimension, but okay. And then we know that it cannot be bigger than the total. That's what you proved.
Yes.
But now we don't know whether other combinations are possible. So we know the total can be much bigger than non-total. Non-total is finite, is 1, and total is infinite. We know that this gap can be arbitrarily large.
Yes. So what I know is that partial can be finite, but effective is infinite. Effective Littlestone dimension is infinite, but partial is finite. So essentially we know everything. We also know that this doesn't imply this. And we also know that, but still, effective Littlestone dimension implies that functions are computable.
So you say that just this information, the non-total is smaller than total and effective is smaller than total, is the only thing we can know. That's what you're saying.
Yes.
And for example, we can have
Another positive thing we have that the effective Littlestone dimension is implies that all functions has to be computed. This is kind of interesting in the sense that, let me say, okay, so I have to basically finish now.
Just say yes or no. Is it true that you essentially proven that for these three quantities everything else is possible? So, for example, it's possible that effective Littlestone dimension is finite, but non-total and total are infinite. And or what any combination of other things is possible. That's what you claim, or not? Что про эти три числа мы ничего другого. Sorry.
Yeah, I understand the question, but I'm not. So what I have shown is that all the relationship between two of them are proved. So I'm not sure. For example, you say, if I want effective Littlestone dimension and partial to be finite and total to be infinite. That I think I don't know. Well, I mean, on top of my head.
Yeah, but for example,
total is fine. Yes.
Any ordering you can enforce. For example, effective is smaller than non-total and non-total is smaller than total. Or effective is smaller than non-total, but non-total is equal to total. Or whatever. So you can have anything you want, yeah?
No, I can't say that without preparation. I don't know. I only thought about the relationship between two. So basically, I was saying that all the things where one is finite and the other is infinite. I understand when it's possible and when it's not for any pair.
Sasha, and can you do, for example, that partial is 5 and effective is 7 or 6?
Partial is finite and effective is
5.
Is equal to 5.
5. No, just some fixed number. Partial is 5 and effective is 6.
I don't know about that.
And the other way around.
No, well, what I can give, say you that I know the example where, for example, partial is 1, effective is infinite. And the other is
effective is 1 and partial is infinite.
No, that's not possible. That's not possible. What possible is that when effective is 2 and partial is infinite.
Okay.
But when effective is 1, then total then total is 1. And hence partial is also 1. Then let me just comment on the most interesting to me, I guess this is this direction. Because effective Littlestone dimension is actually the same thing is to be to be a subset of an effectively closed class of finite Littlestone dimension.
So you say that if effective Littlestone dimension is finite, then all the functions are computable. This is, you say, what is most non-trivial interesting thing.
Yeah, and then, well, this example when the effective is finite, but let's say non-total is infinite is also interesting, but it's easier. But this thing about computable function, I guess it's kind of interesting in the sense that what I'm saying, in other words, what I'm saying that effectively closed classes of finite Littlestone dimension consist of computable functions. But it's not true in general for effectively closed classes. Well, we know that Littlestone dimension classes are countable, right? But it's not true that if I have a Littlestone class, sorry, it's not true that if I have a countable effectively closed class, then it consists of computable function.
Okay, so
So in other words, if you have a decidable tree, you can have countably many subtrees, but one infinite branches, but one will be incomputable. It's fine.
so let me say, ask whether I understand correctly. So you say that there is a nice and non-trivial exercise that if effective Littlestone dimension is at, I don't know, at most 3, then every function in the class is computable. And
Yes.
this you say is non-trivial.
Well, I would hope that somebody will come up with some easy proof.
But you know a proof which is not that easy.
Which is not that easy, yes.
No, if it's not easy for you, it should be quite delicate.
No. I mean, it's okay, but I mean, it's just not just I would expect you to come up with like once.
Yeah, and also it looks counterintuitive because we know that there is no algorithm for depth 4. And somehow from this we should deduce that there is an algorithm that computes all.
No. There is an algorithm for depth 4. For every tree of depth 4, we find something which is impossible. And from this algorithm, we need to conclude that every element is computable.
Ah, right.
But then just you can say some hint. Is the complexity of the algorithm in the conclusion bounded by the complexity of the algorithm in the assumption, or some
because there are
hint?
infinitely many functions. How can it be?
So we need some advice, of course. Yeah. Sorry. And okay, but at least we can try not for 3, but for 2 or 1 and 0, and it should be at some point it should be obvious, but then it should
for
become not.
effective Littlestone dimension 0, it's obvious. That's true.
Yeah.
For Littlestone dimension 1, I mean, it's okay.
And this is written in your paper, which is somewhere in some conference.
So this result is written in some paper, but it's not written in the optimal way. I mean, it's written that it uses some other result. If you apply it here, then you will obtain. And then this result, the other result was written, I mean, some hard version of that result to be accepted to some other conference, not the simplified proof with worse bounds and so on.
Okay, so we can try to make this homework for after your talk, and I don't know, maybe next time we can have Andrei's talk about Ingleton inequalities for line and point.
I think
Maybe.
it's not a good idea because I can explain it, but I think by next Monday I will see online Slava Matveev, who will explain me something else about this argument. So it's somehow
No, but you can start and then you continue later, no? No, if you want to be later, it's okay, but just. Okay, so you may think if there is some other talk for the next Monday.
But why Sasha Kozachinsky can't continue?
Because we probably will not be ready with our homework, no?
So it's not an obstacle, I would say.
Okay. Oh, no, I always like Sasha's talks, but no.
No, but okay, I don't know. I can try to.
But Andrei, do you want to talk on March 10th? I mean, not the next, but next by after the next.
Let us discuss your question in a week.
Okay. So anyway, no Andrei next Monday, and then,
Yeah, and but then we will have to do our homework, and then Sasha will continue.
okay.
But the homework is the content on the top. I mean,
No,
try
but
to
you
prepare
say that there is a complicated thing, and then which is in accepted to several conferences, and maybe some simple one, which is not even. Okay, and okay. Let's think.
Okay, then let's finish today.
Okay, thanks.
Thanks.
Thank you, Sasha.
Thank you.
Yeah.
Thank you.